So in the previous lecture we had stopped at the discussion of so-called tensor product family of shape functions to be used with quadrilateral type of elements, okay, quadrilateral or squares or rectangles. So what we had said is, in defining these shape functions we had looked at the Pascal triangle and we found that this tensor product family gives us more monomials, representation of more monomials than the numbers which are required to give a complete representation of a polynomial of a given order P. So next we had said is, can we, without compromising on completeness, cut down some of these extra terms? And what is the advantage? That in the earlier case, in the tensor product family, if I took, let's say, the biquadratic, then I'll have 9 nodes. That is, I will have 9 shape functions in an element for the tensor product family, which means that in order to represent the finite element solution in this element, I need 9 unknown coefficients to be determined. So if I can in some way sacrifice one of the unknowns, okay, somehow, without compromising on completeness, then my computational task actually becomes smaller, okay, without compromising on accuracy. So that's why we said we'll talk about the serendipity family. Okay, so what I am going to do today is talk of one type of element of the serendipity family, which is the quadratic serendipity element. As far as the linear is concerned, the linear is the same as that you have for the tensor product. So for P equal to 1, I have the same representation as that of a tensor product. Now let us do the quadratic. In the quadratic, what we have is essentially, we are talking of, this is my master element, okay, so it's always in terms of sine eta. So this is the psi line, this is the eta line, psi, this is eta. So I have the 4 nodes at the corners. What I am going to do is add 4 more nodes. That is, from the previous one, for the tensor product, I am removing the interior node. Now I want to define, again using the Lagrangian definition, okay, the shape functions such that they have a value 1 at one of the nodes and they die off at all the other nodes. That is, they become 0 at the other nodes, okay, and they are 0 on this edge. So let's say I number my nodes in this fashion: 1, 2, 3, 4. I am numbering the corner or the edge vertices first, okay, then I am doing the internal one: 5, 6, 7, 8. This is my numbering pattern, okay. So the question is now, how do I construct this shape function? Let's say this is my n1 in the master element. It is 1 here, 0 here, 0 here, and 0 everywhere. So let's now go and do that construction. So in order to do this construction, again we have our nodes, okay. So what we are going to do is talk of these lines. Okay. So from the previous figure, if I see in the psi eta coordinate system, if I am talking of this line, this line is a line which joins the points psi equal to plus 1, eta equal to 0, and the point psi equal to 0, 0, and eta equal to plus 1. Okay, so this is the line psi plus eta is equal to 1. So let's have that line. So this is the line psi plus eta is equal to 1. Okay. Similarly, this line is psi plus eta is equal to minus 1, because this is the point which is which has coordinates psi equal to 0, eta equal to minus 1. This is the point which has a coordinate psi equal to minus 1, eta equal to 0. Similarly, these two lines are perpendicular to these, and we'll have the representation of these two lines as, this one is psi minus eta equal to, so at eta equal to 0, psi is equal to 1. At eta equal to for psi equal eta equal to 0, this is the point. Here this is the point 0 minus 1. So see, when psi is 0, eta equal to minus 1. So this is the equation of this line. Similarly, the equation of this line is psi minus eta is equal to minus 1. This is quite easy to show, that this is the equation of this line is psi minus eta is equal to minus 1. Now I have these four lines. What is the equation of this line? Equation of this line is psi is equal to plus 1. Equation of this line is psi is equal to minus 1. Equation of this line is eta is equal to minus 1. Equation of this line is eta is equal to plus 1. Given these definitions of these lines, can I now construct the shape functions? So let me say I want to construct n1. So this is my, I'll use some numbering, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I want to find n1 hat as a function of psi and eta. This I'll put as c1. Now this function should vanish on which lines to give me the value equal to 1 here and 0 everywhere else. So let's see. If it vanishes on this line, and it vanishes on this line and this line, then it vanishes on all the points other than the first point. So the equation of this line is we'll have psi plus eta plus 1. What about the next one? It should vanish now. Here it has taken care of these points. Now this line and this line. This equation is eta minus 1, and this line is psi minus 1. Okay. So you see that by this choice of these products, I will get this function vanishing at all other points in the element. Okay. How will I find c1? Well, it has to be 1 at the point 1. So I will have n1 hat minus 1 is equal to 1. This is equal to c1 into minus 1 is minus 2, which is minus 1 here. Eta is minus 1, so this becomes minus 2. Psi is minus 1, which becomes minus 2. So implies c1 is equal to minus 1 by 4. Okay. Similarly, if I have to now form, let's say, n7, I can go ahead and form n2. Let's say we'll talk about n2. The shape function n2 will be what? It has to have a value 1 at this point, and it should vanish on all other points. So by the same token, if it vanishes on this line running through the nodes 5 and 6, and it vanishes on the line, top line, which is running through the nodes 3 and 4, and the vertical line which is running from nodes 4 to 1. Then it vanishes everywhere, okay, excepting the node 2. So if I have to write n2 hat, I will write n2 hat is equal to C2 into, it vanishes on this line, so this line will have equation psi plus eta plus 1 into, it vanishes on this line which is eta minus 1, and it vanishes on this line which is psi plus 1. Okay. Now n2 hat has to be 1 at the point, which point? At the point 2, which has coordinates psi equal to 1, eta equal to minus 1. So from there n2 hat at psi equal to plus 1, eta equal to minus 1 is 1, which is equal to C2 into 1 plus 1 2, minus 1 is 1, eta is minus 1, so minus 1 is minus 2, and psi plus 1 is 2. So implies C2 is equal to minus 1/4. Okay. So this way I am going to construct first the corner degrees of freedom, okay, the corner shape functions. So what about n3? n3 again has to vanish on the line joining the points 6 and 7 and the line joining points 4 and 1 and 1 and 2. I am done. Similarly n4 has to vanish on the line joining the points 7 and 8, that is on the line psi minus eta is equal to minus 1, and on the lines eta equal to minus 1 and the line psi is equal to plus 1. So once I have these definitions, it's very easy to then go ahead and construct these corner shape functions. What about an mid edge one? A shape function, let's say function 5, 6 or 7 or 8. So I'm going to form the generic function n7, let's say. So if I want n7, n7 should be such that on this edge, remember on the edge these shape functions should become the standard one-dimensional shape functions of order p. So here if we are talking of quadratic on the edge, if I look at this edge, the top edge, the shape function 4 should look like the one-dimensional first shape function. Shape function 7 should look like the second one, and the third shape function 3 should look like the third one-dimensional shape function. So n2 on this n7 on this edge will look like this. Okay, and then it comes down to 0 at all other points. Okay, so this is how our n7 is going to look. So if I have to make my n7, it should be 1 at this point, it should vanish at all other points. So how is it going to happen? You see that n7 is sitting on this edge. So if I take this edge and this edge, the equation of these three edges, multiply them together, then what it gives me, that this function by the definition is going to vanish on this edge and this edge. I am done. So as far as my construction of n7 is concerned, I am going to make n7 vanish on the remaining three corner edges. So C7 into, so it vanishes on the edge, this edge is psi is equal to minus 1, this edge is eta is equal to minus 1, this edge is psi equal to plus 1. So I will have psi plus 1 on the edge eta equal to minus 1, eta plus 1 on the edge psi is equal to minus 1, plus 1 is psi minus 1. This is it. Also I want my n7 hat at the point, which point? At this point, point 7, which has coordinates psi equal to 0, eta equal to 1. So I want at 0 and 1, this is equal to 1. This is equal to C7 into 1, 2 and minus 1. Implies C7 is equal to minus half. Okay. Similarly, I can construct n8 what will n8 be? n8 has to vanish on this edge, and on this edge, okay, on this edge, and this edge, which means n8 will vanish on the edge eta equal to -1, psi equal to +1, and eta equal to +1, okay. And by the same token, I can find the constant C8. So if I can do these things, okay, I have constructed the 8 shape functions corresponding to the serendipity family, okay. So let us now look at one of these shape functions and look at the expansion. So my n7 hat, if I look at it as a function of sine eta, is equal to -12 into eta plus 1 into psi squared minus 1. This is -12 into eta psi squared minus eta plus psi squared minus 1. Let us look at n1. n1 hat as a function of psi and eta will be equal to -1/4 into, if I do this one, it will be psi plus eta plus 1 into eta minus 1 into psi minus 1. So it will be psi eta minus eta plus 1 into psi eta minus psi minus eta plus 1. Okay. So I will get, if you see here, what is the bottom line, that I will get something like psi squared eta, I will get eta psi eta squared, I will get psi eta, I will get psi, I will get eta, then I will get psi squared, I will get eta squared, and I will get the constant. If I expand all these things up, some constant into, some coefficient into these terms. So you see that it contains the linears, it will contain the linears, it will contain the quadratics, and it contains these two extra terms, psi squared eta, psi eta squared. So if we go back to our Pascal triangle, the Pascal triangle was, if you remember, in terms of sine eta, 1 psi eta, psi squared, psi eta, eta squared, psi cubed, eta cubed. Okay. So if I look at this, so the Pascal triangle for the quadratic will have only this part. This part is completely represented by our serendipity family, plus it has some more terms which are these terms. So the serendipity family has now 2 extra terms as compared to 3 extra terms which we had for the tensor product family. Similarly, when we go and define, we can easily now continue this job and talk of the serendipity family of order 3. Okay. Then in that case, again remember that the shape function should be such that on the edge they should represent the given order 1D shape function. So I will construct them using the 3 points, the 4 points on the edge, okay, like this. Okay. So in this case I will have how many points? In this case I will have 4 p terms. Okay. So the number of shape functions corresponding to this is 1, 2, 3, 4, 1, 2, 3, so on, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So I have 4 p shape functions, which is for p equal to 3, 12. If I had taken the tensor product, I would have actually p plus 1 into p plus 1, which is p plus 1 squared number of terms, which for p equal to 3 would be 16. If I had taken triangular elements, then I would have p plus 1 into p plus 2 divided by 2, which would be 10 terms. Okay. So if I had used triangular elements of order 3, okay, I would get 10 functions to solve for, 10 unknown coefficients in each element. If I use tensor product of order 3, that is bicubic, I would need 16. If I use the serendipity of order 3, I will need 12. Okay. So depending on what cost you want to pay, okay, one can use one type of functions or the other. Okay. Now we have defined basically the major families of shape functions that will be needed to start off any finite element computation in 2 dimensions. So the next job is that given these shape functions, now I can have the u finite element, okay, in the element tau written in terms of psi and eta in a generic element is given in terms of I is equal to 1 to number of degrees of freedom in the element, okay, ui tau for the element, ni hat as a function of sin eta. Okay. This is the representation in the element. Okay, my question is, what is a global representation? Let us say I have a domain with 4 elements. Okay, let us talk of the serendipity. So let us say I have a serendipity which is quadratic. Okay, I formed this element domain or the mesh of 4 elements of quadratic serendipity. I decide to number the degrees of freedom as 1, 2, 3, 4, 5, 6, 7, 8, 9, and I will call these 10, 11, 12, 13, 14, 15, 16, then I will come here 17, 18, 19, 20, 21. Okay. So in my 4 element mesh that I will have 21 unknowns when I use, total number of unknowns is 21 when I am using the serendipity quadratic shape functions. And I have deliberately done this kind of a numbering so that I first number the corner degrees of freedom. The reason being that remember that we are doing, as far as the mapping of the geometry is concerned, the geometry is always mapped using the bilinear map. It does not matter whether I am using the tensor product family or the serendipity family, I am always using the bilinear map for the geometry. That is, I started off with a polygonal domain or even a non-polygonal domain, but in fact polygonal domain, so that all edges of all the elements are straight edges. That is, my elements are initially quadrilaterals, not with curved edges, okay, with straight edges, and these are mapped to these master squares. So for that, this bilinear map is good enough. Okay. So let us say I am talking of polygonal domains. What do we mean by polygonal domains? Well, one domain is right in the picture, another domain I can have is this kind of a domain where all edges, bounding edges, are all straight lines. Okay. So here you see that I have the total finite element solution is given as UFE is equal to sigma I is equal to 1 to 21 UI phi I. Okay. My question is, what is this phi I? So what is this phi I? If I look at the fifth one, for example, the phi corresponding to the fifth global node, remember that by our definition the phi's are defined with respect to the global nodes. So if I look at the fifth phi, it will be 1 here, it will die off like this in this element, and then it becomes 0 on these edges. In this element it will have this kind of a behavior, okay. Now in this element it will have this kind of a behavior, and then it will vanish here, it will vanish here, it will vanish here. So this phi is like this kind of a tent, okay. Similarly, by piecing together these element shape functions, now we can have the global phi definition, which we have discussed many times over, so there is no ambiguity. Now given this, we also have to now construct the local to global enumeration. So let's say I am talking of element 2. For the element 2, let me go and do the local enumeration. So the local is 1, 2, 3, 4, 5, 6, 7, 8. Okay. Which global ones does it correspond to? It corresponds to, if I go back here, the 1 of element 2 corresponds to 2, global 2, the 2 corresponds to global 3, 3 corresponds to global 6, 4 corresponds to global 5. So 1 corresponds to global 2, 2 corresponds to global 3, this corresponds to global 6, this corresponds to global 5. Okay. Then what does the 5 correspond to? Global 14, 6 corresponds to global 15, 7 corresponds to global 16, and 8 corresponds to global 11. So it is 14, 15, 16, 11. Okay, note one more thing, that what I did first is I went ahead and numbered these corner degrees of freedom, then I started looping over each element, and I started numbering for the first element all its side degrees of freedom. I am giving them global numbers. So first I had the 9, then I added 10, 11, 12, 13. Then I come to the second element, look at the first side, look at the mid side degree of freedom. Has it been numbered? No. Give it a number, 14. Next side, numbered? No. Give it a number, 15. Next side, 16. Come to the fourth side, it already has a number, retain it, don't increment. So this way we go ahead and construct the numbering for the degrees of freedom. One can choose many other ways, but I have chosen like this. Okay. So this correlation is our global to local enumeration, or local to global enumeration. Okay. And this will go in again, as we had said, in something called the ILDOFS array, where I will essentially stack one below the other the degrees of freedom, the correspondence of the degrees of freedom at the local level to the global level for each element. Okay. So here in this I will say, okay, the local 1 for this element corresponds to global 2, local 2 corresponds to global 3, and so on. So this I am going to do in such a way that the stack of the 8 degrees of freedom for the first element is put first, then the next 8 corresponds to the second element, then the next 8 corresponds to the third element, and then the fourth element. So in this actually we will have stack of 8s, because every element has 8 degrees of freedom defined at the local level. And then through suitable pointers we can address these locations, find out the local to global enumeration. Okay. So this detail, this information, as we had done in the 1D case, has to also be constructed in the 2D case. So armed with this information, now for any generic element which is either a serendipity type or the tensor product type, we can go ahead and compute the entries of the stiffness matrix for the element, which is integral over the area of the element tau. We have taken the simple this thing definition of the model problem. So I'll have del ni, del x, del nj. This is for the tau, del x plus del ni tau del y del nj tau del y. Okay, dA. This, as we had said, is equivalent to doing the integration of the master element tau hat of del ni, I will say del ni tau del x, del nj tau del x plus del ni tau del y del nj tau del y, now represented as functions of sin eta. Okay, these are represented as functions of sin eta into the Jacobian into dA hat. And again, what will happen to this dA hat? It will become an integral of psi going from -1 to +1 and eta going from -1 to +1. This integrand into the Jacobian into d eta d psi. Okay, so standard way of getting these integrals now in terms of the master element. And as usual, as we had done before, I need to find this del ni tau del x is equal to del ni hat del psi del x plus del ni hat del eta del x. These things, these quantities can come out easily from the definition of the shape functions. So when you are defining the shape functions, at the same time we will define the derivatives of the shape functions with respect to sin eta. Okay, so your shape function routine should return you the value of the shape functions and the value of sin eta for a given point sin eta. These quantities we have to get from where? From the mapping. Okay, and remember that serendipity or tensor product, p order anything, we are talking of only linear maps of the geometry. Okay, the mapping is independent of the order of approximation for the problem cases that we are talking about. Okay, so this, where will it come from? As we had done in the previous class, that our dx deta is equal to del x del psi del x del eta del y del psi dx dy is equal to del y del psi del y del eta d psi d eta. And now this is so called Jacobian matrix. These quantities we can compute by using our bilinear mapping, that is x in terms of x1, x2, x3, x4 and the sine functions of sin eta. Similarly, y in terms of y1, y2, y3, y4 and functions of psi and eta. So then simply we can write d psi d eta, and look, this function Jacobian is now going to be a function of sin eta. So then this will be equal to Jacobian inverse into dx dy. Now this Jacobian inverse is actually equal to del psi del x del psi del y del eta del x del eta del y. Okay, so by having these components, finding Jacobian inverse is very easy. That is 1 by Jacobian, change these terms, change the sign of these terms, I get these quantities. Okay, this we have discussed many times, I am not going to repeat it. Now these are going to be functions of the given sin eta. Okay, so at every point I evaluate these quantities from this inverse mapping, and that's why you see that the inverse mapping should have the Jacobian greater than 0. Otherwise what will happen, this can become singular. Jacobian can become, that is, the determinant of the Jacobian matrix can become 0, and the inversion may not be possible. That is, many points are going to one point or vice versa. That is, the mapping is not one to one anymore. Okay, so that's why we need to have the shapes of the elements or the quadrilaterals in such a way that the angles are always less than 180 degrees. Okay, so with all this, now we can determine these quantities at every point, and the only question is now, how do we go ahead and put it in a program? Okay, in a program we will have to set it using, do the integration using integration points, that is, replace the integral with a summation. Before going there, let's now talk about how to apply the boundary conditions. Let's say on this edge I have given some kind of a flux boundary condition. I should not be drawing it like this. On this edge I have specified G. Okay, G is specified. This edge lies in the element 1. Okay, so if I look at element 1, okay, we are going to number the edges for the generic element in terms of the local nodes. These are the local nodes for the element 1. This is going to be my edge 1, this is going to be my edge 2, this is going to be my edge 3 and edge 4. What do I see? My edge 4 of element 1 has the G specified. So then, as far as the integral is concerned, remember that I have to integrate G against Ni tau ds on this edge 4. Okay, on the edge 4, and remember the ds will be like this. Okay, this is what I have to do as far as the integral is concerned. So how do I do it? Okay, this edge, if you see, corresponds to, in the master element, this will be corresponding to here psi is equal to minus 1. Okay, so what do I have is actually, and again on this edge, which shape functions are non-zero for the element? If I am using the quadratic serendipity, okay, then it will be the first one for the element is non-zero, okay, the fourth one for the element is non-zero, and the eighth one is non-zero. So only these shape functions are going to participate as far as this integral is concerned, and on this edge these shape functions are the 1D shape functions. So why can't I say that on this edge the shape functions are now Ni hat as a function of psi I am going to put as minus 1 and eta. So they become a function of psi and eta, but psi is equal to minus 1. So they are left as functions of eta only. So here I am left with these guys being functions of, I will call them Ni double hat of eta. Okay, so I map it to this master edge. On the master edge I look the edge of the master element, I find that this is a function of eta. Now the problem is that we have to simply do the integration with respect to eta, but since this direction is downwards, we will have to integrate for eta is equal to plus 1 to eta equal to minus 1. Okay, ds is nothing but then, or if I integrate from eta equal to plus 1 to minus 1 to plus 1, ds will be actually minus d eta. In this case, that's what I am going to do. Okay, so this integral of this quantity g as a function of eta on this edge into Jacobian for this edge d eta. Okay, and I start from the point this. Sorry, ds is minus d eta. Okay, I am done. So with this, I go ahead and do my integral on this edge. Similarly for the other edges, if the boundary condition is specified. So I essentially do the projection, remember, and integral, which is the 1D integral. So this way I can construct the integrals on the edges of the elements, and once I am doing the element calculation, as I compute integral of r ni hat d psi d eta into the Jacobian, okay, over tau hat, I will, after doing this, I am going to compute the boundary integrals if the edge lies on a Neumann boundary, and simply add the integral to these corresponding entries, and I am done. Okay. For a generic edge, if I have, let's say this is an edge, okay, here how do I find, and let's say my S goes like this, okay, then you see that this has point x1 y1, this has point x2 y2, okay. For this edge, my ds is equal to square root of dx squared plus dy squared in terms of length, okay. So then ds is equal to this, which is equal to square root of dx ds whole squared plus dy ds whole squared ds Jacobian. Okay. So what we are saying is this is equal to this quantity. The Jacobian is equal to this. Actually, I should have written it as dx d psi d eta d psi, and here I should have d psi. So ds is given in terms of d psi, and this is nothing but the scaling of the lengths, which is the Jacobian for the edge. This is not the same Jacobian as that for the area. Okay. So this way I can complete all my integrals that we have to do for the element, and I can go ahead, given my local to global enumeration, we can assemble the stiffness and the load vector components in their respective global stiffness and the global load vector entries Ku and F, apply the essential boundary conditions by fixing those known degrees of freedom to the known values, okay, and go ahead and solve. So I should be able to solve the complete problem. Okay. Now the question is that how do we go ahead and do the integration? So integration in a computational domain will involve numerical integration. Okay. So we'll give it, here we'll discuss the integration rules for triangles and quadrilateral elements. So for a triangle, remember that we are doing the integral in the case of a triangle over the master triangle. Okay. This is 0 0 1 0 0 1. Now I want to replace integral of some sine eta d psi d eta over tau hat is equal to summation over j is equal to 1 to number of integration points, okay, f evaluated at these points psi j eta j into a weight function corresponding to these points. Okay. This is what we would like to do, replace it by a summation. So if I take this, now the question is that depending on the integrand, the order of the integrand, remember we are dealing with polynomials only here defined over the master element, then the integrand, the polynomial order will define what order integration rule I should use and how many points would give me an exact integral for that given order. So the number of points, okay, is fixed by the order of the integrand. Okay, so order of the integrand fixes the number of points. So what we are going to give now is a sample Fortran routine which gives these integration points for triangles, which, by the way, construction of these points for triangles is not so easy. This is something which is obtained from a research paper written long ago, about in the 1970s, okay, on how to obtain these points for triangles. So this is a routine called setInt, which, what does it do? You input to it the order of the integrand. The order of the integrand we have to compute from the integral, the terms involved in the integral, which is exactly the way we had done in the 1D case. One has to go and find this order. Given the order of the integrand, it returns the values of the coordinates of the integration points for this particular order and the corresponding weight function through veta. Okay. So the way things are arranged in this page are that I have an array giving the coordinates of the shape functions of the integration points, and a vector weight which gives me the values of the weight functions. Okay. If you see here that if my order is equal to 1, then we will see something very interesting. In that case, for order equal to 1, my weight function, the weight has a value 1. That is, first of all, for this order equal to 1, I have one point integration rule. That is, there is only one point for which the weight is equal to 1, and the xint is now given, has 3 coordinates, but we had only sine eta. These 3 are actually given in terms of what is called the area coordinates or the barycentric coordinates, okay, which is very simple. That let's take any point, okay, and this is my node 1, node 2, node 3. Connect these points. This becomes my area A1. So given any point in the middle or anywhere inside the master triangle, I connect that point to the 3 vertices. The area opposite to a given vertex is given the name A1. This area becomes A2. This area becomes A3. Now I know that A1 divided by A plus A2 divided by A plus A3 divided by A is equal to 1. So these quantities are given names as lambda 1, lambda 2, lambda 3, and this, you see, for any point you can define unique values of lambda 1, lambda 2, lambda 3. So this is sometimes referred to as the barycentric coordinate system. Okay, this was classically used when triangular elements were used. Now we are writing everything in terms of sine eta. It turns out that if you see, look at lambda 2. Lambda 2 is 0 when I am on this edge, and when I have a point on this edge, and it is 1 when I have the point here. Okay, when the point is here, then lambda 2 is 1. Now, which of our psi's and etas is 1 here, 0 here? So lambda 2 is actually equal to our global psi. Similarly, lambda 3 is actually equal to a global eta, and lambda 1 is nothing but 1 minus psi minus eta. Okay, fine. So it's quite easy to relate these barycentric coordinates to our sine eta, that lambda 2 is the psi, lambda 3 is the eta. So as far as we are concerned, this is our psi, this is our eta. So whenever you see these 3 points given, they are given in terms of the lambda 1, lambda 2, lambda 3 corresponding to this integration point. So we are only interested in the sine eta values. That will do our job. Similarly, if my integrand is of order 2, a polynomial of order 2, then you see that we are going to have actually a 3-point rule, that when the integrand is of order 2, then I have 3 points involved, okay, and the weight of the first point is 1/3, weight of the second and third point is 2/3 and 1/6, okay. Similarly, the coordinates are given like this. So the coordinates of the points, the other 2 points of the first point is psi is equal to 1/6, eta is equal to 1/6. The weight of the second point is also 1/3, weight of the third point is also 1/3. So weight of the second and third point is 1/3, and the coordinates are inherited in this way. So this way I can keep on continuing and create the integration rules of the requisite order. For example, when the order of the integral is 3, then I think I have a 4-point rule. So you see that there are 4 points involved, and the weights and the coordinates are given like this. The weight of the first point is this, weight of the second point is this, weight of the third point is the same as the second point, and of the fourth point is the same as that of the second point, while the coordinates are given as these, okay, in terms of the barycentric, which we can easily convert to our psi eta form. Similarly, when the order is 4, then you see that in that case, for the 4th order rule, I'll have 6 points, okay. So there are 6 points in the, that is NINT for order 4 is equal to 6. So you see here the number of points is not, cannot be obtained directly as a formula in terms of P. Here we have, it's a little bit complicated, but nevertheless we have these points available to us, and you see that they are given, the coordinates are given in 3, 3, 6, 9, 12 up to the 15th decimal digit. So they are given in double precision. So one can use these points and define the integrals, the integration rule for a triangular element, okay. So what we have now obtained is, we have obtained essentially all the modules which are required in order to do a finite element computation in 2D, okay, for the single variable problem, okay. So let's come down to what we were doing earlier. That fine, we have defined the integration rule for the triangles. How do we define it for the quadrilaterals? For the quadrilaterals, life is very easy. In fact, I have the psi and eta directions like this. You see that here psi is equal to -1, here psi is equal to +1. Here on this line eta is equal to -1, eta is equal to +1, okay. So what I do is, I take the product or the tensor product of the 1D integration rules for the psi direction and eta direction, and that is going to give me the integration rule for the 2D. 1D rule is already known. So let's say, how are we going to make it? If I have a linear in psi and a linear in eta, okay, as my integrand, okay, so it's a bilinear integrand, that is linear in psi, linear in eta, then the rule is governed essentially n is equal to p plus 1 greater than equal to p plus 1 by 2, okay. So if it is, and where p is in each direction, what is the order of the p, okay. So if p is equal to 1 in the psi direction, 1 in the eta direction, then essentially p plus 1 is 2, 2 by 2 is 1, so I can have a 1-point rule. Now for the psi in this direction, the 1-point rule corresponded to the point psi equal to 0. In the eta direction, this 1-point rule corresponds to the point eta equal to 0, okay. So for us, for our element, we take the corresponding coordinate as the one which has psi eta equal to 0. Okay, and what is the weight function? So essentially I will take psi I 1d eta j 1d as my psi I eta j, okay, corresponding to the ijth, I am giving a double index integration point, okay, and the weight for this point is equal to weight I 1d into weight j 1d, okay. So it's as simple as that. That is, that integral over psi is equal to -1 to 1, integral of eta going from -1 to 1 of f, which is a function of psi eta d eta d psi, is equal to summation of I comma j going from 1 to n, okay, f at the point psi I eta j, okay, into wij, okay. This is my integral for the quadrilateral elements. So it's as simple as that. So I replace the summation, the integral by the summation, where the summation is understood as summation in the psi direction, that is a cross product of or tensor product of the psi and eta directions. So I have the 1D functions which we have already created in the 1D problem. We can easily construct the 2D functions. So let's take the case for the 2-point rule. So in the 2-point rule, if you remember, it corresponds to psi eta is equal to plus minus 1 by root 3, okay. So psi is plus minus 1 by root 3, I think so. Eta is also plus minus root 3. So I will take our integration points as in the 2D domain as this. Our integration points are going to be this, 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 this. Where this is my psi 1, this is my psi 2, this is my eta 1, this is my eta 2. This is my psi 1 eta 1 point, this is my psi 2 eta 1 point, this is my psi 2 eta 2 point, and this is my psi 1 eta 2. And the weight here is W1 into W1, weight here is W2 into W1, weight here is W2 into W2, and weight here is W1 into W2. Done. So this is how I can do the integral. So we have essentially defined how to do the numerical integration inside the area, okay. In the next lecture, we are going to look at some of the properties of the finite element solution that we have obtained as far as convergence is concerned. As far as how to improve the convergence, we will just talk about those things of the finite element solution, because that's very important in the 2D case, because the domain itself, the shape of the domain itself, the geometry, is going to decide to a large extent the smoothness of the solution.